Okay, continuing on with compound events. So, we can't use the area model if there are 3 different events occurring. So what can we do? The model that was mentioned before is that we can do a tree diagram. So this is an example that's pretty nice for that. So we're making cakes. We've got 2 base flavors of cake to choose from, and then 3 icings and 4 various toppings. So this can be pretty nicely set up with a tree. You can see a tree diagram very quickly gets very messy, so I highly recommend making a nice full tall page handout for the first time that students try to do a tree diagram to keep them organized, especially if fine motor skills are an issue. This can be really difficult. But it's a nice model, so I feel like it's worth working through it. So if we take a look at our potential possibilities here, it's really nice if you choose words without the same first letter, so you can V for vanilla, C for chocolate. So our first branches into our 2 different possibilities and cuts all of them in half. And then with my next one here, I've got my buttercream, a possibility, fudge, and whipped cream. And then those 3 choices with the split down below. And then again, strawberry, blueberry, candy corn, and kiwi. And I can continue to label all of those through. So something that's nice about this tree diagram is you can make a case for multiplying all of your different possibilities together to see how many outcomes there are going to be in the first place, to sort of have students start to build a picture of that in their minds. So there are 2 different branches, 2 different choices for the first one. So my first decision, I've got 2 different ones to choose from, and that breaks it into 2 different places. So that doubles all of my possibilities. My vanilla possibilities and my chocolate possibilities. And then from there, from each of those, I got 3 branches. And so if we stopped there, we would have 2 times 3 through 6 different outcomes. And then if we add, if we put on the topping, then from each of those branches, we've got another 4 possibilities. And that gives us our 24 different outcomes that we can see at the end of each of these branches. And so we follow the branch along to find out what our outcome is. So here's our cake with vanilla, with buttercream frosting, and with strawberry topping. So our vanilla buttercream strawberry cake. And that exact cake is 1 choice out of 24. So there's a 1 out of 24 chance of getting that cake in particular. So this again supports the idea that we multiply our probabilities together, because if we look at our probability of cake flavor, 1/2, if we randomly select our flavors of, what kind of cake are we going to come up with? Well, it's a 2 choices, so 1 out of 2 for vanilla, 1 out of 2 for chocolate. And then 1 out of 3 for each of these. And then 1 out of 4 for each of the last branches. And if we multiply those together, following the path, 1/2 times 1/3 times 1/4 does equal our 1/24th probability. So that is a strategy that can be built, and that idea built with this picture. And we can also ask questions such as, what is the probability of getting a cake at random that has strawberries as the topping? Well, one strategy, one way to use this table is to look at, there's 1 out of 24 probability of getting this cake with strawberry, 1 out of 24 for this one, 1 out of 24 for this one, 1 out of 24 for this one. Same here and same here. So we've got 6 24ths as our possibility there. And that reduces to 1/4. And so we look at our situation and see where that comes out in the picture. Well, if we are just looking for the probability that the cake has strawberries on it and we don't really care what the cake flavor or icing is, there is a 1 in 4 chance of the topping being strawberries, and so that connects right there. So that goes back to our 2 rules for compound events. We've got the first one, if it's either or. Anytime we're doing or, for example, if we're looking for the probability of drawing king or queen, then it's adding. We're adding 4 kings out of 52 plus 4 queens out of 52, giving us 8 out of 52, reducing to a 2/13 probability. For 2 independent events that we're looking for both, an and in particular is happening. So we're looking for both a 1 and a 6, which is the same idea as 1 then 6 occurring. We've got a 1 out of 6 probability, and we multiply 1/6 times 1/6, and we've got our 1/36. To the tree diagram for one more note. This is a nice place to introduce the term mutually exclusive to students. If I was to say that my favorite cake has fudge topping on it, and that my sister's favorite cake has kiwi topping, I guess mine fudge icing and my sister's kiwi topping, then I could list all of the potential cakes that would be my favorite, and we could list all of the potential cakes that were my sister's favorite, and we can say that they are not mutually exclusive because they have 2 different cakes in common. There would be 2 cakes that would have both my favorite and my sister's favorite. Those would be a vanilla fudge kiwi cake or a chocolate fudge kiwi cake. It would make both of us happy. Another thing that I just have to mention for probability topic is more and more I find that students are having a really hard time with decks of cards. I actually have to teach my students what the composition of a deck of cards is, which is really hard because a deck of cards is a very wonderful tool for practicing and talking about probability, but if there's not familiarity, that's kind of tough. The last thing is you can't talk about a probability class without mentioning the Monty Hall problems. Let's take a quick look there. A very engaging activity or task to work through is the stay or switch game. It's a game that can be played and that has some pretty interesting probability to look into. So you're playing a game, and at the end of every level there are 3 boxes. One contains 10,000 points and the other 2 are empty. You're allowed to choose one of these boxes, but before the one you choose opens, one of the other boxes is always open to show that it is empty. So then your choice is, do you stay with your first choice or switch to the other unopened box? So there's 3 boxes. It's box A, B, and C. Suppose you choose box B. Before the box opens, one of the other boxes is open to show that it is empty. Imagine in this case the empty box is C and it is opened. So the game allows you to stay with your first choice or switch to the other unopened box. So the question is, should you stay or should you switch? So this is a really nice question to play with students and then have them grapple with the different possibilities. And then finally have them explain proof of their thinking and how they could make sense of this. And it's an awesome task. It covers 4 of the math practices: making sense and persevering, reasoning abstractly, and constructing viable arguments, and modeling with mathematics. And it's also based on a real-world situation. It's based on the Monty Hall problem from the old television show Let's Make a Deal. So a nice way to look at the solution is to use a table showing all of your possibilities. So you could set it up with starting with, well, what if you stick with the strategy of I'm going to keep my box, and look at your outcomes each time. So if my strategy is I'm staying, and I've got here's the table of all the possibilities. If the 10,000 is in box A and I choose A, then I win. But if it's in box A and if it's in box B and I choose A, then I don't win. If it's in box C and I choose A, then I don't win anything. So there are 3 possible favorable outcomes out of the 9 total. Well, the possibilities with switching are a little bit better. Let's say I chose box B, but the 10,000 points is actually in box A. Well, I'm sitting at box B, and so the computer is going to open box A. And so if I switch, I still get my 10,000 points. I'm going to win. So switching actually changes the probability, because one of the 3 boxes is revealed to be not the one. So, I mean, there's still the chance that you chose correctly in the first place, but your chances are greatly increased if you switch boxes, and specifically 6 different ways to win out of the 9 total. So it's a 2 out of 3 chance. Another way to look at that is to look at the abstract reasoning. When you know nothing about box A, B, or C, there's a 1/3 chance. And as soon as one of the boxes is revealed to be the wrong one, then you've got a 2/3 chance after switching the strategy. One of them ends up being revealed. So anyway, this is a fun activity to work through, and really wonderful for having students. It's difficult to explain and get students to truly understand the explanation. It's difficult for a lot of people. So it's a really good one, especially for constructing viable arguments and critiquing reasoning. It on probability. So and that's it for this video. I'm going to move on to another one where I'll start talking about random sampling.